this combined concept example, we are going to look at a roller coaster car that's currently unpowered. So it's just kind of going along the tracks. There's no additional motor or anything like that. And it goes through the circular shaped dip of radius r. And then it's all frictionless, and it goes through that circular dip in the road, and then it goes up the ramp of length d. So the total length along the ramp here is going to be d. And it flies off the ramp and onto a large giant cushion, which catches its fall. And they want to make the car land safely. Where do they need to place the cushion? So finding L. And what speed will the car hit the cushion? So we are told here, one of the pieces of information is that the normal force at point A is going to be equal to 6, oops, I'm moving it around, is equal to 6 mg. So where m is the mass and g is the magnitude of the acceleration due to gravity. So that's a bit of given information. And we again want to find L, and we want to find the speed at which it's going to hit the cushion so that they can make sure it's not too fast and that the cushion is in the right place. Okay, so we have to then think about how we're going to go about solving this. So we are given the normal force at a particular location in a circle. So that means that we're going to use Newton's second law with the normal force to get the speed, and I'm going to label that point A, to get the speed at point A. So let's call that step 1 so we can keep track of it. Then once we know the speed at point A, then what we're going to do is, and I'm going to label another point here, point B, we're then going to imagine we are then have this change in height, and so we need to figure out what's the speed at point B. So again, a change in height is very often a conservation of energy step. So we're going to use conservation of energy from A to B in order to get the speed at point B. Then what we can do is from point B to where it hits, which I'll call point C, this portion is going to be just our standard 2D projectile motion, and it's an angled launch. So I'm going to say use 2D constant acceleration. Another way to talk about that would be projectile motion. And there we're going to get both L and the magnitude of the final velocity vector, which is what speed is. All right, so let's go ahead and work through this. What we will see for Newton's second law with the normal force at the top at the bottom is that for step 1, we want to draw the free body diagram. So we're going to have the normal force up. We're going to have mg down. It's going to be accelerating towards the center of the circle at that given point. So the acceleration here is v squared over r. Little r is given to us. And so we want to find v. So we can say n minus mg, the sum of forces in the vertical direction, is equal to mv squared over r. And I'm going to call that v sub a because that's telling me that's the speed at point A. Subscripts can be very useful with these combined concept problems. And so then n, in this case, we were told that was equal to 6 mg. So 6 mg minus mg equals mva squared over r. So what's that going to allow us to do is basically then we can cancel out our m's. We end up with 5g times r. So the speed at A is equal to the square root of 5gr. I'm going to box this as an intermediate step. Now I want to do my conservation of energy step. My conservation of energy from the bottom where I just found the speed to that higher height. There's no springs, there's no friction. So it's really straightforward conservation of energy step, where I'm going to then say conservation of energy. I'm going to have my kinetic initial, and I'm going to take that to be my lowest point, so no gravitational potential energy, is going to be equal to K final plus UG final. So I can now plug in for these. So I have 1/2 m VA squared, so that's the speed I just found, would equal to 1/2 m VB squared, that's the speed I'm trying to solve for, plus mg, and then the height here, and you can see that the actual height change between A and B is r. So mg r. So now I can plug in for solve for VB and plug in for VA. So VB squared, I'm going to cross off my halves and add a 2. My masses cancel everywhere. So VB squared is equal to VA squared minus 2GR. So now I can plug in for my VA. VA squared would be 5GR minus 2GR. So that gives me 3GR. So the speed at B is going to be equal to the square root of 3GR. And again, I'm going to box that as a key result from the result of that conservation of energy step. So now I know the speed at point B, and that's going to be the speed, and I'm given the angle at which it's launched at. So now I can move on to my 2D projectile motion. So in this case, I like to kind of draw my diagram. There's my speed, there's theta. This whole thing, we were told, was a height h off the ground. And so we want to find L as one of the things we're trying to find. And we also want to find the magnitude of the final velocity vector, because that's going to be what our speed is. So I can write down what I know in the x and the y direction. In the x direction, I do know my initial velocity, and remember in x it stays the same, it's constant. So VB times the cosine of theta. Now I don't necessarily know the time that it's in the air, so that's going to have to come from the y direction. So over here, I then can write and start my equation by saying delta x, which is what we want, is equal to Vx times t, so Vb cosine theta t. And so what that tells me is that to get delta x, I need time in the air. So now I need to go over to my y direction. My acceleration is negative g, as it always is in y. My initial velocity, Vy initial, will be Vb, and it's positive because it's an upward launch, Vb sine theta. And then I know my height. I'm going to take that y final equals 0 at the ground, and that y initial is going to be equal to h. And so in this case, I have a couple different ways to go about solving this. I could use the quadratic and solve for time, and then use that to get delta x. I might do that to start. The other thing is that I realize that I also want to find Vy final. So Vy final, and I need time to get delta x. So I have two goals in y, and I can kind of do whichever one I'd like. I'm going to solve for Vy final first because it'll allow me to avoid the quadratic. So Vy final squared is going to be equal to Vy initial squared plus 2a delta y. So y final minus y initial. And so now I can go ahead and say Vy final squared equals Vy initial squared. So Vb squared sine squared theta minus 2g, and then y final is 0 minus y initial, which is h, so 0 minus h. And then there's going to be a trick here that's really important. So this is going to be vb squared sine squared theta, and then plus 2gh. And when I want to take the square root of this, note that I'm going to take the negative square root because it's going to be heading downward. My Vy final is downward. So Vy final is going to be negative, and then it'll be the square root of Vb squared sine, oops, I lost my squared, sine squared theta plus 2gh. I'm going to put a squiggly line under that. It's not yet my end result. And so now I have a couple things I can do. First, let's just get the final speed, because that was one of our key results. Final speed, remember, would be the magnitude of the final velocity vector. It's not just in the y direction or in the x direction. It has to be the square root of vx squared. Vx final is vx initial is vx, so vx squared, plus vy final squared. So this is going to, again, look messy, and that's okay. So the final speed then is going to be, remember, Vx was Vb cosine theta. So this is going to be equal to Vb squared cosine squared theta plus Vy final squared. So the negative goes away, again, because it's in this particular portion of it. Vb squared sine squared theta plus 2gh. So this is my final speed. So they could then, go back and solve for these. We know Vb. So again, this is where we can write where Vb equals the square root of 3gr. So that means that this would be equal to 3gr cosine squared theta plus 3gr sine squared theta plus 2gh. Good. So that's going to be a final result. I'll go ahead and highlight it. And then also we need L, which is equal to delta x. And so that's then going to be equal to Vxt, which was Vb cosine theta times time. And so I'm going to plug in for Vb now. So square root of 3gr cosine theta times time. And again, I need time for this. So what I can do is then just use the first equation. V final in y equals V initial in y. And then plus acceleration times time. So time equals V final y minus Vy initial all over acceleration. And this is where the fact that I needed to take Vy final be negative in order to get the right value here. So Vy final is shown at the top. And so Vy final would be negative, oops, I need to change back, negative square root of Vb squared sine squared theta plus 2gh. So that's Vy final, I made it negative, minus Vy initial, which was Vb sine theta. And then I put that all over A, over negative g. So my negatives are all going to cancel out. And so my time is going to equal this ugly thing. And I'm doing these ugly ones so that you get kind of used to it. You can see me working with it. There was some requests to see more of these ugly algebraic answers. And you see, you just sort of plop it all down and just leave it in there. And it's okay. So now I can come back here. Let me change colors to kind of show where I'm at. This is delta x. So I just need to plug this time in for time here. And so let's go ahead and do that. And I then get that L, which is again equal to delta x, is the square root of 3gr times cosine of theta times, and then I'm going to just turn all of those to pluses, times this ugly, ugly thing, which is the square root of VB squared sine squared theta plus 2GH plus VB sine theta all over G, and that's all multiplied together. So if you were designing this roller coaster, you would have these general equations. You wouldn't just sort of randomly calculate it for one number and then try another number and then try another number. You'd come up with a general expression that described the thing you're trying to design, and then you could play around with the radius here. So you would then be able to play around with the radius of the circle. You'd be able to play around with the angle of the ramp, and then the height of the ramp. And all of those would allow you to make a safe version of this roller coaster. Okay, let me know if you have any questions.